Okay, so hi, welcome to the second lesson of quantum field theory. Um, and today I'll talk about mainly about the interaction picture, which is something that we will use in canonical quantization of QFT. So this is under the canonical picture. So remember there are two pictures, right? One is the path integral the path integral, sorry, perhaps not the best word. One is a path integral method, and another one is a canonical method. So this interaction picture will be relevant for the canonical method. And then we also talk about a bit of classical field theory. So let me find the slides. Sorry, the slides are a bit non-linear. So let me, okay. I've also been working on a resource for the Feynman propagators, but I didn't manage to get it out in time. So I'll try to get it out. I want to do a nice table where I can show all the contours. So I plan to have a case where you have the two cases t less than t prime and t greater than t prime, and then you have the four cases of the contours that go around the post. So I plan to make a nice table to make it much clearer what kind of integrals we are doing. And yeah, so but I haven't got that done yet. Okay, so let's try to talk about classical field theory today. And this is also related to a question that Jeb uh asked previously about the question he asked was when I showed in my slides, I actually integrated over four momentum, and then I integrated over e to the minus ikx, where this is the four momentum times it's a contraction from the four momentum with the fourth position. And then the form that he roughly showed was something more like d3 to the p, and then 2 ep, and then something e to the ip dot x, something like that. So I'll resolve the ambiguity today. And it turns out that the two of them are actually equivalent. So I'll show how they're equivalent. So after doing classical field theory, I didn't manage to get out the canonical quantization slides in time, but I'll show the steps that I have settled so far lah. Yeah. Okay, so let's begin first with I think let's begin with classical field theory, because it'll give a bit more context for what we're doing later in the interaction picture. Okay, so in classical field theory, let me see. Okay, so let me just erase all these. So previously, where we left off was when we had a class in a classical theory, we write down a Lagrangian, and the Lagrangian would tell us how to calculate the action. The action is the integral of the Lagrangian with respect to time, and we want the principle of least action tells us that the fields would satisfy Euler-Lagrange equation, which is the differential equation involving the Lagrangian. And in the case where we have the free scalar field, which is this Lagrangian, we get the following Euler-Lagrange equation. And this equation was something that when we expanded phi in Fourier space, right, we got the following relation, which basically tells us, which basically saying that the energy of a particle must be square root of the momentum squared plus mass squared, which is we might recognize this as the relativistic dispersion relation. Yeah, so this equation over here is sometimes known as the on-shell condition. In other words, particles that are real particles that are solutions to the field equations, to the Euler-Lagrange equations. Those are like in some sense real particles that exist. So in other words, field configurations that satisfies the on-shell condition, right, which is this condition. Field configurations that satisfy this relation, the particles that exist, they can live for very long. And we may be wondering, is that all the particles that can exist? Is there ever cases where you can have fields that do not satisfy this on-shell condition? And the answer is yes. Actually, when we study, when we put the action in a path integral, so if you do integral over all of the fields e to the is of this, right? If you expand this out and you expand this out in terms of a experiment, one can actually see that there are cases the so-called particles that you get do not satisfy the on-shell condition, and those are known as virtual particles. So sometimes you hear that in quantum mechanics you often hear the saying that in a empty box, right, there's actually a quantum soup of particles where you have a particle and an anti-particle pair popping in and out of existence. So they pop out, right, with some due to some energy fluctuation. They call it quantum fluctuations, and then they actually annihilate each other in a very short period of time. So that's roughly what these virtual particles are about. Yeah, so it turns out that these virtual fluctuations would be responsible for the 0 point energy, which is sometimes known as the vacuum expectation value, VEV. So sometimes will be calculating whenever we have an operator, let's say A, right, we'll be interested in the vacuum expectation value, VEV, and that's basically the expectation value of this operator with respect to the vacuum. In this case, vacuum meaning there's no real particles. So this is something that we'll eventually be calculating. Okay, so so this is known as the on-shell condition. Now, this for real, at least in classical field theory where there are no quantum fluctuations, this condition must hold true. Fields that exist physically, they must satisfy this condition. If not, they wouldn't satisfy the Euler-Lagrange equation. So essentially, in order to enforce this condition, we put a Dirac delta in our field expansion, meaning that previously we had this, right? We postulated that the fields can be expanded in terms of Fourier modes, just this term and this integral. But when we integrate over all four momentum, right, we're looking at the space of all values of the vector k, right, all r to the four values. But we actually do not want that because the m over here is a fixed parameter in the Lagrangian, and where we know from this condition that this must be satisfied. So the four momentum must actually satisfy this condition. So we put a Dirac delta over here to basically restrict the momentum that we integrate over. And this is basically saying that we only want fields phi that satisfy Euler-Lagrange, right? We only want those for classical field theory, we only want the fields phi that satisfy the Euler-Lagrange equations. If not, they're not real, they cannot be physical fields. So we put this condition over here, and this, remember, the Dirac delta is a function that is basically if you it's basically 1 or infinity. Some people, I think let's call it it's infinity when x equals to 0, and it's 0 when x is not 0, right? But when you integrate it over, even though it's infinity over here, when you integrate over dx, right, you get 1. And this is made rigorous in the theory of distributions. So this over here basically tells us we're integrating over all four momentum, but we're only selecting the momentum that satisfies this equation. So there is actually a nice identity. So inside here, we see that it's not of a nice form like delta of x, right? It's not something like delta of k where we can actually get rid of some integrals. We can actually get rid of one variable of integration. So what we need to do is we need to transform the inside of this Dirac delta using the following identity. Yeah, I quote this identity here without proof, but if you study theory of distributions, it will make more sense. And this identity tells us that the delta of f of x, in order to calculate the delta of f of x, right, is equivalent to finding all the zeros of the function, right? And for each of the zeros of the function, we need to calculate this quantity over here. So in this case, remember that k is 4 numbers. So k is 4 numbers, right? So if we split the first component and the rest of the components up into k naught and k vector, right? The arrow, meaning the spatial component, spatial vector part, then we can write it like that. And the reason why I want to split it this way is because later, for this 4 momentum, right, I want to essentially get rid of the d to the k naught integral. I want to get rid of this integral to give me a resultant d to the 3k. And I want to get rid of the time component because because I because it's the most, it feels the most natural to want to get rid of. So I split it up this way because I want to eventually integrate out k naught. So if I split it up this way, I get the following, right? Where ek is defined to be, where ek is defined up here. So ek is defined to be the positive square root of this. Okay, and so this can be split into 2 roots, and then if you differentiate this quantity over here with respect to k naught, then you get the following expression. Is this step clear? Equation 1, 2, 1. Everything okay? Yeah. Okay. So if not, then we can now substitute the above expression, right? We have for that into this over here. But before that, right, we're actually going to do something. We're actually going to take the complex conjugate of the field, the real field. And the reason why I'm doing that is because I want to show eventually that if I plug in a minus k, right, is equivalent to taking the complex conjugate. So I eventually want to show this. So how do I show that? Right, I take the complex conjugate. We see that oh, okay, sorry. This probably shouldn't be here. It's a typo. Okay, yeah. Let me just get rid of this. So if we plug in, if we take a complex conjugate, we see that okay, we take the complex conjugate, then we see that let's assume, let's say this phi of x, we don't know whether it's real or complex first, right? Let's say it can be a complex field. Then we take the complex conjugate, this e to the minus ikx will flip over to ikx, and then this component, right, which we don't know whether it's real or complex yet, it will need to pick up a complex conjugate. So this just as good as saying the complex conjugate of a sum of components, right? Because the integral is a sum, is equals to the sum of the complex conjugates, right? And then after that, okay, so over here we see that we have an integral over k, and then we have e to ikx. We can actually relabel it. We can actually relabel the integration with minus k. So if we integrate over minus k instead, then we get the following, and k prime can be, it's just a label for the integration, right? It's just a label for the sum. It's like if I have sum over I, it's just this label I can change it to any other name as I want. So if I do that, then it gets turned into the following expression. So now if we compare, we see, yeah, any questions? Hello. Hi Sunny, welcome.
Oh,
Yeah.
hello.
So now, hello, yeah. So if we replace this and this, right, we're comparing e to the minus ikx phi of k versus e to minus ikx phi star of minus k. So now if we impose if we want to impose that phi of x must be a real field, then the two of these must be equal. And if the two of these are equal, then that must imply that each of the Fourier components are equal, because it's as good as comparing two vectors. So you may be wondering if this 2 is equal, right? If the left hand side of here is equal, why does it imply that each of the components are equal? It makes more sense if you think of in terms of Fourier space, meaning that you think of the phi as a you think of the phi as a vector in the function space, and then if this is also phi star, right? If the two of them are equal as vectors, then all the components must be equal, right? If I expand it in terms of a basis, in this case, the basis being e to minus ikx, the Fourier basis. So once again, this is it's very useful to think of functions as vectors in some function space. So this is referring to infinite dimensional linear algebra. which is very useful when you talk about quantum mechanics in general and physics. So yeah, so okay, so we know that phi of x is if we want it to be a real field, then this is a condition, and this will become useful later. Okay, so going back to what we're doing just now, we wanted to insert the Dirac delta of this thing into the Fourier expansion for the real field phi, and after that we substituted it for this expression. Now what is nice about this is that we have k naught, right? Is in terms of k naught minus some quantity. So the integral essentially now splits into it splits into two, right? So one piece being this one and one piece being this one. So for this one we basically substitute. We see that over here the d to the 4 becomes d to the 3. So the k naught variable is integrated out. So 1 over 2 ek is put out in the denominator. So so the integrand, right, which is this guy, we are basically substituting k naught for the first term over here. We're substituting k naught equals to ek into the expression. So phi of k becomes phi of k becomes, this was the 4 vector. Now phi of k becomes phi of ek and the k vector spatial components. Yeah, and then now e to the minus ikx, right? Remember that this was a contraction over 4, so it becomes e to the minus ik and then bracket ekt minus k vector dot x vector. All right, and that's what we see over here. Likewise for the other term, just that instead of having ek, right, I have minus ek because that's what make this term inside the Dirac delta 0. Okay, following so far? Okay, if there's any question, you can just feel free to interject. Yeah. Okay, so now, right, we're going to do something nice, and that is, okay, so over here, okay, let me just clear out some of the annotations. So over here, the next step we're doing, we're actually flipping the sign. If we observe the differences, it's actually we're flipping the sign of k vector to minus k vector. And likewise over here, minus k vector to plus k vector. So essentially what's happening over here is that this integral has two parts, right? The first one being this one, and the second one being the second integrand. So this one, I leave this untouched. Right? This one just copies over. But this one, because I'm integrating over all momentum, right? All the R3 values, right? For k vector, I'm integrating over all three R3 values. I can essentially do the same trick as I did just now and write k prime equals to minus k, right? And I integrate over that and then I just relabel it. So it's as good as replacing k with minus k, right? As vector k with minus k vector. So that's what brings me from this step to this step. And why do I want to do that? Is because if we observe over here, now ek and k, right, they are the same sign. Minus ek and k minus k vector, they have the same sign as well. And moreover, we even see that now this term, right, is this term over here is kx, right, contracted as the four vector dot product, and this one becomes and this one becomes ikx. So this one is minus ikx and this one is ikx. So that essentially gives me this expression. So with phi of x equals to this, and yeah, so this is so yeah, so I managed to basically express. Previously I had a integral over 4 momentum, right? Previously I had phi of x. The whole point of this is that previously I had phi of x equals to d4k e to the minus ikx, right? Where this is a 4 vector thing, phi tilde of k, where this is also a 4 vector. so previously I had this expression where it was an integral over 4 momentum, but now I have an integral over 3 momentum, and uh, uh yeah, now I have an integral over 3 momentum. So and the things I also picked up my 2 to the k over here. So this supposedly ties in nicely um with all the expressions you see on this fine, I think it's called Klein-Gordon field. So yeah, so if I check up, right, this one, we see that we have yeah, so this is what we see. And it's also important to note something, and that is that yeah, so we see over here that this expression matches up with the last expression over here. But there's something to note, which is that we see over here a of p and b of p. They seem to expand it in two types of coefficients, and sometimes they say that a of p is the particle and b of p is the antiparticle. Because a of p is the positivity and b of c part. So where do we see this? We see it in these values. So these values, they are they are independent of each other, because they're independent of each other. They're independent of each other because we are we're integrating. Yeah, because this one corresponds to positive ek, and this one corresponds to minus ek, right? This is, we substitute in ek over here and minus ek over here, and ek is positive, right? Ek itself is positive. So ek is positive because we defined it up here to be ek, we defined it to be positive. So essentially, these two components are corresponding to the positive ek, right, and the minus the frequency. This one is the frequency is positive ek, and this one, the frequency is minus ek. That's what they mean by positive and negative frequency components. Oh no, my Zoom link would end in 10 minutes. I'm not sure why. Let me just double check. Okay, that's a bit weird. Yeah, okay, it's okay. I will. Okay, never mind, never mind. When it ends, I'll create a new link. Okay, so okay, we know that the positive frequency and negative frequency components are independent of each other, because these can be any functions we want, right? However, there is something to note, which is that if we want the field to be real, if we want the field to be real, then they are complex conjugates. Wait, sorry, does this make sense? Yeah, if we want the field to be real, then they're complex conjugates of each other because of this condition over here. And essentially what that is saying is that if we want the field, if the field must be real, right? So actually, okay, so let me just say it clearly. So this one is the positive frequency, right? Omega equals to plus ek component, or coefficients, right? Coefficients for the field. And then we have phi minus k equals to the negative frequency, right? Namely, we have omega equals to minus ek coefficients. And by right, if we don't impose any condition, right? If there's no condition on phi of x, right? If we do not require it to be, meaning it can be a complex field, then these so it can be complex, right? If it can be complex, then essentially these are phi of k. I can't seem to write for some reason. Then phi of k. Oh, if there's no condition on the two of them, then phi of k and phi of minus k right, are independent. They're completely independent of each other. They can be any numbers. They do not talk to each other at all, right? And this corresponds to antiparticles and particles, right? Existence of antiparticles and particles. The particles being this guy, and the particles being the first one, and the antiparticles being the second component, the minus k components. Yeah, so that's if the fields can be complex. However, if we impose that phi of k, sorry, not phi of k, phi of x must be real. If we impose that phi of x must be real, then we actually get that phi of minus k must be related to phi of k, right, by a complex conjugation. And this condition basically tells us, this condition essentially is telling us that um, a, a creation, when we promote these to operators, right, complex conjugation, when we promote these to operators, complex conjugation, right, becomes a Hermitian conjugate. So essentially this is saying phi of k dagger equals to phi of minus k. And this is known as a destruction, right? Or annihilation, annihilation operator. And this one is on the right is known as creation operator. So when they are upgraded to operators, then a field being real will in some sense imply that uh the 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 creation of a particle is equivalent to the annihilation of an antiparticle. So yeah, so that's a field being real, essentially uh essentially relates particles with antiparticles in a way that uh essentially makes it impossible to makes it impossible to have antiparticles having a a life of their own. Yeah. Um yeah. Okay, so so the key idea over here was to summarize what I've just said just now, right? And then I think I'll call a quick end to this meeting because not because and then I'll open up a new meeting link because this one is running out. I didn't know that there's a time limit. So okay, to summarize what we have just talked about so far is that we talk about the on-shell condition, k square minus m squared. This is the on-shell condition. And fields in classical field theory, right? Fields that satisfy the Euler-Lagrange equation must satisfy the on-shell condition. And if we want if we want to expand phi of x in terms of momentum space, e to the minus ik x phi of k, phi tilde of k, right? Then it doesn't make sense to expand it freely over all four momentum, right? Because we only want to expand over the four momentum that satisfy k squared minus m squared equals to 0, the on-shell condition, the Euler-Lagrange equation. And in so doing, right, we essentially found out that it can be expressed over a integral over 3 momentum, right? Because this essentially restricts k naught to be a specific value of equal to plus minus ek, and that integrates out the k naught degree of freedom, the k naught degree of the integral over k naught, right? We restrict it to be certain values, so now it is fixed. So that will give us integral over 3 momentum with this extra factor of ek, and actually that implies that this is actually, as they say, is a Lorentz invariant measure. And okay, 2 more minutes. So if we expand it out like that, then we actually get minus k ikx phi of k and e to the ikx phi of minus k, right? right, tilde or minus k. And then the last part we talked about imposing, if we want a real field, if we want a real field, then phi of k must equals to phi of minus k, must equals to phi of minus k complex conjugate, right? If we can allow the field to be complex, right, then these are phi of k and phi of minus k is independent. And this roughly corresponds to, right, having anti particles in the theory, right? Complex fields will turn out to be related to anti particles. So yeah, so okay, I think that's a good place to pause for now, and I'll send a new Zoom link. Yeah, okay, see you guys in a minute. Any questions? Okay, thanks. Let me just end the meeting temporarily.